Wire antennas, half-wave dipole, series on antennas and wave propagation, lecture number 2.12. Half-wave dipoles are straight conductor antennas with length equal to lambda by 2, one half-wave length. These are first antennas that has ever been used by mankind to establish wireless communications along with loop antennas. These are simple, easy to analyze, easy to design, and also quite easy to understand. In the present session, we focus on the structural features, the electrical characteristics of these antennas. We begin the analysis with the finding of field intensity in the radiation given by this antenna. From field intensity, we determine radiation intensity, directivity, effective aperture, etc., which are important performance indicators of this particular antenna. And then we move to folded dipole, which is a variant of a half-wave dipole. It is designed to have more radiation from the antenna than given by half-wave dipole. Radiation resistance of folded dipole is more than half-wave dipole, indicating that there exists more radiation in folded dipole when compared to half-wave dipole. Folded dipole comes into being when one or more arms are added to an ordinary half-wave dipole. We discuss about the input impedance. We discuss about bandwidth enhancement. We also discuss about applications of folded dipoles before closing the session. Let us begin the session by considering structural features of half-wave dipole. Half-wave dipole is a thin, straight wire conductor of length equal to lambda by 2, and it is usually center-fed. It is an important wire antenna. It is used as a gain standard. It is used as a feed to lens antennas and parabolic reflectors too. We have to keep in mind that it is a wire antenna. Its variant is a folded dipole. This folded dipole is used as the driven element in Agee-Oda array. Agee antenna is popular as a domestic TV receiving antenna. Dipole radiates maximum in a direction normal to its length. If this is dipole, radiation is maximum, normal to its length, and nil along its length. In this direction, along the length of the dipole, radiation is 0. Normal, it is maximum. The radiation is linearly polarized with the E vector parallel to its length. It radiates equally in horizontal plane, hence its pattern is a circle in this plane. One can say that radiation is omnidirectional as far as half-wave dipole is concerned. Some more points. In vertical plane, radiation is maximum normal to its length, falling to 0 sinusoidally as we move along its length. Its vertical plane pattern is dumbbell in shape. The pattern is omnidirectional, which is already mentioned. In vertical plane, the pattern appears like this. In horizontal plane, it is circle. This is dipole. At resonant frequency, its input impedance is supposed to be pure resistance and low. For a practical dipole, input impedance can be found as 73 plus J43 ohms. Normally, it is considered as a 73 ohms, but exact value is 73 plus J43. Reactance part is also there. When the excitation frequency is less than resonant, its impedance is capacitive, and it is inductive when frequency is more than resonant frequency. These are all important aspects. Before going further, it requires to be mentioned that dipole is a resonant antenna. It belongs to the category of resonant type of antennas. A few points regarding formation. The structure and current distribution on a half-wave dipole can be derived from a parallel wire transmission line. This is parallel wire transmission line. Two conductors are there. If the line is open circuited at the load end, here open circuited, and excitation is connected to the other end, this side excitation. Standing wave pattern comes into being over the length of the line with a current node exactly over the load end. This is load end, it is open, therefore current is 0. So here current node exists here. Now open out the line at a distance of lambda by 4 from the load end and bend them in opposite directions until they are aligned while simultaneously moving them closer. So you consider a point which is at a distance of lambda by 4 from the load end, this point. So now current will be maximum at this point because it is at a distance of lambda by 4 from node. Current maximum exists. Now to form half-wave dipole, what we need to do is you move the conductor, top conductor upwards, bottom conductor downwards until they are vertical like this. This is 1 lambda by 4. This is another lambda by 4. Now move these conductors near to each other as much as possible. The resultant structure is half-wave dipole. The current, one can see here current at the ends it is 0, at the middle it is maximum, varying in a sinusoidal manner. We now have the structure as well as current distribution over half-wave dipole with us. By transferring the current distribution over to the bent aligned conductors, half-wave dipole results with a sinusoidal current distribution having maximum at the center and 0 at the endpoints. After having some idea regarding structural features, current distribution over half-wave dipole, now we undertake the analysis of half-wave dipole. In the analysis, expressions for far fields, radiated power, radiation resistance are determined. This is the purpose of analysis. To find far fields, radiated power, radiation resistance. Radiation resistance indicates the efficacy of the antenna as a radiator. The analysis is undertaken in phasor domain, and the sequence of steps followed are same as that of analysis of short dipole or elementary dipole. Of course, only difference is short dipole or elementary dipole has been analyzed in time domain, but here we are doing it in phasor domain. To go further in the analysis, place the dipole over z-axis with its center at the origin. Then the current can be expressed as I of z is Im cos beta z. We have just seen current varies in a sinusoidal manner. Maximum at the center, 0 at the ends. So corresponding expression becomes cos beta z. When dipole is placed along z-axis, centered over the origin. This is phasor domain current. It is supposed the field point is located far away from the source. Actually, what we want is far fields. Far fields exist or far fields dominate only when field point is located far away from the source. Distance of the point under consideration, field point, has to be large, where radiation fields dominate. As the current is entirely in z direction, magnetic potential A can have only z component. The procedure, as already mentioned, is the same as that of procedure followed during short dipole analysis. From current, vector potential is determined. From vector potential, magnetic field intensity. From magnetic field intensity, electric field intensity. This is the sequence. The analysis requires the antenna to be fixed over a particular coordinate system. Now it is known to us that in antenna theory, widely used coordinate system is spherical one. The dipole is placed over z-axis in spherical coordinate system. This is lambda by 4. This becomes minus lambda by 4. This is observation point or field point. This point is far away from the radiator. So R is large, capital R, small r is also large. This is theta polar angle. Small r is radial vector of a spherical coordinate system. It represents vector from origin to the observation point. Capital R is vector from differential element over the half-wave dipole to observation point. Capital R, small r. These are vectors, but they are different. Each one has their own individual meaning. Over the radiator, a small length is considered at a distance of z from the origin. Differential length dl. As it is along z axis, it is dz. dl is dz. Capital R is vector joining dz to observation point. First, we consider small length radiator dl equal to dz. From that, we slowly move to find field intensity due to this radiator at point P, field point P. First, we try to evaluate A. A stands for vector potential. As current is entirely in z direction, potential, vector potential also, it remains entirely in z direction. Az is equal to mu Im by 4 pi integral minus lambda by 4 to plus lambda by 4 cos beta z e power minus j beta r over capital R dz. See, this is the expression for vector potential. Here integration is there. To evaluate the above integral, certain approximations called far field approximations are made. Otherwise, difficult to evaluate this particular integral. R, capital R, magnitude. Capital R denotes vector, whereas its magnitude denotes distance. This distance is related to small r, and cos theta through r minus z cos theta is capital R. Sometimes we can also approximate capital R is small r. Magnitudes. Both the approximations are with respect to their magnitudes. The first one is used in phase term and second one is in distance term. Out of these two approximations, the second one is a somewhat crude term, crude approximation. First one is more sophisticated, more near to the reality. But second approximation, it simplifies the solution process more. If we use first approximation, even in the second one, that is distance term also, then things become quite complicated. That is one aspect. Second aspect is the second approximation cannot be used in the phase term because it leads to a lot of error. So first one is suitable, requires to be used while dealing with the phase term while evaluating the integral, and second approximation has to be used while dealing with the distance term while evaluating the integral, that is capital R. This is phase term. Notice this is phase term, whereas denominator one is distance term. Now Az is equal to e power minus j beta r mu Im 4 pi r integral minus lambda by 4 to lambda by 4 cos beta z e power minus j beta z cos theta dz. How this expression has come from the first one? Capital R is in the numerator replaced by r minus z cos theta. Capital R in the denominator is replaced by small r. It results in this term. Moving further, Az is equal to mu Im e power minus j beta r over 4 pi r into e power j beta z cos theta over beta square minus beta square cos square theta into j beta cos theta cos beta z plus beta sin beta z. Limits are minus lambda by 4 to lambda by 4. This is after integration. Now limits minus lambda by 4 to lambda by 4. These limits are required to be substituted. It results in Az being equal to mu Im e power minus j beta r over 2 pi r beta cos pi by 2 cos theta by sin square theta. This is superfluous. We all know mu is permeability of the medium. Im is current at the center of the dipole. R is radial distance. of the field point from the origin. Beta is phase shift constant to 2 pi lambda. So somehow we are able to have an expression for z component of vector potential. We want to do the analysis, further analysis in a spherical coordinate system. So what we do is we convert Az into spherical components, AR, A theta, A phi. Az can be resolved into R direction and theta direction. AR becomes equal to AZ cos theta, A theta becomes equal to minus AZ sin theta, A phi becomes 0, HR can be found 0, H theta also can be found 0. How? There is a connecting relation between mu H equal to del cross A. H and A are vectors. A is known once AR is available, A theta is available, A phi is available. Substituting these components in del cross A and doing the necessary differentiation, finding the curl and equating the three components with the three components of H. Mu H, one can find HR 0, H theta 0, but H phi it is not 0. H phi, mu H phi can be found equal to minus sin theta dou Az by dou R. We have to substitute Az in this expression and perform differentiation. Then we get an expression for H phi. Once H phi is obtained, E theta can be found without any difficulty because we are computing radiation fields. Radiation is a TEM wave. In TEM wave, E by H is equal to eta. For free space, eta is 120 pi. It gives us E theta by H phi is equal to 120 pi. Once H phi is available, E theta can be determined by considering the product of 120 pi H phi. So H phi is available. It is because Az is available. Once H phi is available, using that expression E theta can be found. We get E theta as 60 Im e power minus j beta r over r cos pi by 2 cos theta by sin theta. How this thing has come into being? H phi is minus sin theta over mu, minus sin theta over mu dou Az by dou r. Az has already been available to us. Now substitution of Az in this expression and performing differentiation, ultimately we have this one. In this expression, notice e power minus j beta r is there. This is phase term. If we want magnitude, we have to consider the remaining part of the expression. 60 Im over r cos pi by 2 cos theta over sin theta. This is magnitude. This is the radiation field intensity due to half wave dipole. The above expression can be given a graphical form. It appears like this. This is a half wave dipole. It is placed along z-axis. For half wave dipole, this is the pattern. For isotropic radiator, this is the pattern. In the horizontal plane, it appears like this. In the vertical plane, as already mentioned, it is in a dumbbell shape. Once the radiation field intensity E is available, remaining quantities, interested quantities can be computed without any difficulty. For example, radiation intensity, it can be found from the connecting relation between intensity and field intensity. S is equal to E square by 2 eta. Here S is power density. First power density can be calculated. E is available, so power density can be obtained without much difficulty. Once power density is available, radiation intensity, which is R square multiplied by S, can be computed. In the present case, it turns out to be 1 by 2 eta, 60 Im cos pi by 2 cos theta whole square, 1 by sin square theta. Similarly, radiation resistance can be determined. Power density is available. Total power radiated can be found from power density. How? This is radiator. Consider a spherical surface with the radius r. Power density at a distance of r is available. This is the expression. So S is available. Now integrate S over this surface. it gives total power crossing the surface. The power crossing the surface naturally is equal to power radiated by the radiator, which is of course total power radiated by the dipole. And equate this total power radiated to I square RMS into R radiation. It gives R radiation as 73. Similarly, directivity can be determined. Directivity is given by 4 pi U max by PT. PT is already available while doing radiation resistance. We have determined PT. U max can be found from the expression U, which we have already done while computing radiation intensity. Maximum value of U is U max. Substitution gives us a D as 1.64. So half wave dipole directivity is 1.64. Radiation resistance is 73 ohms. Standard values. Beam area. Beam area can be determined in two ways. One way is omega A is equal to 0 to 2 pi, 0 to pi UN, normalized radiation intensity sin theta d theta d phi. This is one way. UN is available, normalized radiation intensity. Substituting that expression here in this relation, one can get it as 4 pi over 1.64. This is one way of finding beam area. Another method is also there. Omega A is always equal to 4 pi by D. This is universal relation. In this way also one can determine. We have already seen directivity as 1.64. The simple substitution gives omega as D. Effective length can be determined. Effective length is 1 over Im integration over length and IDL. So here I is Im cos beta z dz. Length spans from minus lambda by 4 to lambda by 4. Performing this integration, doing this integration gives effective length of half wave dipole as lambda by pi. Effective area. Effective area can be calculated using this expression. This is one way of finding. Another expression, another way is also there. Effective area is lambda square by 4 pi into D. Directivity is available. It is 1.64. Simple substitution gives AE as lambda square over 4 pi into 1.64. Another way is also there. If we want to do it from fundamentals, that way is 120 pi effective length square by 4 radiation. Radiation resistance is available. Effective length is available. Substitution gives, of course, same value, 1.64 into lambda square over 4 pi. Half power beam width. Half power beam width, the angular separation between half power points for half wave dipole can be found as 78 degrees. Note that this is the bandwidth measured in vertical plane. In the horizontal plane, it is omnidirectional. The beam width becomes irrelevant. See, as far as the horizontal plane is concerned, this is the radiation pattern. Here, beam width is irrelevant. Same amount of radiation in all directions in this horizontal plane. So beam width is relevant only in case of vertical plane where pattern is like this. Plane pattern is like this. So here one can identify half power points. Let us say here and here. The distance between them, angular distance, can be determined. In the present case, it turns out to be 78 degrees. Now we move to a variant of half wave dipole, that is folded dipole. First, what is folded dipole? It is a variant of half wave dipole. What for folded dipole? The purpose is to have more radiation from half wave given by half wave dipole. So how it comes into being? This is half wave dipole. Add an arm, additional arm to this, and connect this arm at the end points. Now what we have is folded dipole. Another arm also can be added. Another arm can also be added. Several arms can be added to half wave dipole. Addition of arms, you are going to see, increases amount of radiation from the dipole, folded dipole. So a few important points regarding a folded dipole. A description for folded dipole antennas was first given by P.S. Kata in 1939 in a paper titled Simple Television Antennas. It is a broadband resonant antenna with bidirectional radiation pattern with the maximum radiation along the normal to the length of the arms and no radiation parallel to their lengths. It is essentially two dipoles in parallel as far as the radiation fields are concerned. Its radiation is linearly polarized with the E vector parallel to arms of the dipole. Pattern is similar to half-wave dipole. Its functioning can be understood very easily. So this is half-wave dipole. It radiates maximum normal to its length. Let us suppose it is radiating certain amount. If we place a similar antenna near to this dipole, another dipole, if we place it like this, then this second one also starts radiating. The radiation by the second one normally gets added to the radiation given by the first, provided the distance between these two dipoles is negligibly small. When radiations get added naturally, it results in more radiation, more radiative power than given by a single dipole. The resultant structure is termed as folded dipole formation. It consists of two closely spaced half-wave dipole elements connected together at the outer ends. See, this is one dipole, this is another dipole. Notice first one is fed conductively, second one is fed from the first one. After being fed from the first one, both start radiating. It can be formed by pulling the conductors of a shorted half-wave length parallel wire line apart from their midpoints. The currents in the two conductors are equal in magnitude and phase when their radii are same. Here is shown a folded dipole in A, ordinary folded dipole B, a folded monopole. This is folded monopole. It is a half of a folded dipole located over a ground plane. C is shown a multi-element folded dipole. Three elements are, this is first one, second one, third one. Equivalent circuit of folded dipole. The equivalent circuit of folded dipole consists of a combination of antenna mode and a transmission line mode with separate voltage polarities and current directions. Both the elements of the dipole carry both modes of currents. He is talking about two element folded dipole. Two element folded dipole means like this. The antenna mode currents are in the same direction, whereas transmission line mode currents are in opposite directions. In the two elements of folded dipole, antenna mode currents are in phase, whereas transmission line mode currents are out of phase. In the two elements of folded dipole, here is shown folded dipole. This is source. 2A is dia of the conductor with which folded dipole is made. L is length. Usually it is lambda by 2, nearly lambda by 2. Functionally, it is equal to two folded dipoles. One is transmission line mode dipole, another is antenna mode dipole. Transmission line mode, you can see currents. Here current is upwards, here current is downwards. In the same way, we can see here current is upwards, here current will be downwards. So currents are in opposite directions in the two elements. This is transmission line mode. When it comes to antenna mode, current here is Ia by 2 upwards. Here also it is Ia by 2 and upwards. So currents are in the same direction. If you consider bottom wise also same thing. This is as far as currents are concerned. When it comes to voltages, it is plus minus minus plus. But here it is plus minus plus minus. So antenna mode, transmission line mode. Together is folded dipole mode operation. At the resonance, the antenna mode currents are relatively large, being equal to V by Rin, equal to V by 4 R radiation resistance in each element at the center, but 0 at the ends. Whereas the transmission line mode currents are 0 at the center, but have the value IT equal to V by 2 Z naught T at the ends, where Z naught T is characteristic impedance of each of the two shorted quarter wave transmission line sections. The folded dipole exhibits very high input impedance, which can be further increased by connecting additional arms to the dipole. See, more high input impedance means more radiation resistance. More radiation resistance means more power in the radiation. more power in the radiation means the signal can reach far away points too. The distance between radiator and the receiving antenna can be larger and larger. Range can be more and more. It is an advantage. It's a plus point. So high input impedance to an antenna is always sought after quantity. The input impedance of an n-arm folded dipole is equal to product of square of number of arms and impedance of the ordinary dipole. This is standard formula, widely used, most popular formula. Zin of a folded dipole with n arms is given by 72 into n square. Here n is number of arms. In this diagram is shown folded dipole. In A, currents over the dipole. This is dipole currents. In the earlier diagram, we have shown the currents separately. Here, both the currents, antenna mode current, transmission line mode current, both are shown over the same antenna. In B is shown bandwidth compensation. What is bandwidth compensation? Inherently, folded dipoles are broadband in nature. This broad bandwidth can further be increased by adopting certain techniques. These techniques are called bandwidth compensation techniques. So, bandwidth compensation means enhancing the bandwidth of the dipole antenna. Bandwidth compensation, a few points are given here. Inherently, folded dipole is a broadband antenna. Because of its geometrical arrangement, one arm tends to behave as a short parallel stub line which attempts to cancel the off resonance reactance of single dipole. Bandwidth can be further increased by compensation techniques like connecting short-circuited lambda by 4 transmission line or parallel LC circuit to tune out the reactance across the antenna terminals. At a resonant frequency, the dipole resistance is in parallel with the input impedance of transmission line, which is very high. Above resonance, the antenna impedance is inductive and the line impedance is capacitive, obtaining compensation. Below resonance, antenna impedance is capacitive and line impedance is inductive, so that compensation is again obtained. So by connecting a short-circuited lambda by 4 transmission line or a parallel LC circuit, one can have more width from folded dipole. Now, applications of folded dipoles. Folded dipoles and their derivatives, they are well known for high input impedance and broadband characteristics. Find several applications. Some of them are given here. They are used as driving elements in Aggie-Oda arrays for their high input impedance and broadband characteristics. They are also used for television signal and FM broadcast reception. They can also be modified to form T-match antennas whose impedance is 600 ohms. With this, we come to an end to the present session. To recap, in this session, we spend some time on the structure, the electrical nature of half-wave dipoles. We have undertaken the analysis of half-wave dipole to find its radiation field intensity, radiation density, radiation intensity, directivity, beam area, effective length, etc. of half-wave length. And then we moved to understand about a variant of half-wave dipole, that is folded dipole, its important features, its bandwidth compensation techniques, its applications, all are discussed before coming to the end of the session. Hope this session is useful to you. We meet again in another session soon with a new topic.